Hi everyone, I'm Tristan, and I'm very proud to introduce my new baby ISOLDE. The name stands for Interactive Structure Optimization by Local Direct Exploration, but the simplest description is that it's a new interactive model building environment. In particular, it's designed to ease the often fraught task of building and refining models into low-resolution maps. So before we get properly started, I'd like to spend a minute or two discussing why that's important. There's quite a lot going on in this plot, so let me break it down for you. On the y-axis, we have the mole probability score, which combines common measures of structural error, namely atomic overlaps or clashes, unlikely backbone conformations, and unlikely sidechain conformations, into a single log-scale score, where lower is better. On the x-axis, we have the R-free, a measure of how well the model fits the data. Again, lower is better. So the bottom left corner is where we want to be. Each spot represents one 3.5 to 4 angstrom crystal structure deposited in the last decade and is colored by resolution from blue for 3.5 to yellow for 4 angstroms. The problem here isn't just that few models are in that bottom quadrant, but that it appears that in this resolution range the correlation between model quality and fit to data, which I should emphasize is very strong at high resolutions, has broken down essentially completely. In other words, a very poor quality, physically impossible model can fit the data much better than a more realistic one. The picture is essentially the same when we look at cryo-EM models in the same resolution range, except that in this plot the bottom right-hand quadrant is where we want to be. A somewhat problematic situation. So, how can ISOLDE help to fix it? To answer that, I'll start by taking you through the essentials using my favorite toy model in the absence of a map, then show how it all can be applied in a real-world situation. Here we are in Chimera X, the platform upon which ISOLDE is built, and I've opened up a model of insulin-like growth factor 1. ISOLDE currently supports protein, DNA, and RNA models. Metal ions and water molecules may be included but should be handled with care. All residues, including any water molecules, must be complete, including hydrogens. Hydrogen atoms can be conveniently added using Chimera X's built-in addh command. To run ISOLDE, you'll need a recent Linux machine with a GPU capable of OpenCL or CUDA processing with up-to-date drivers. Support for Mac and Windows environments is in development. To get it, within Chimera X, go to the Tools menu and then click More Tools to enter the Chimera X toolshed and follow the links to download and automatically install ISOLDE. Once installed, it will appear under Tools, General, ISOLDE. So let's fire it up. The interface loads as a floating window. If your computer has two screens, I recommend putting it on the second, but here I'll dock it into the tool area on the right. For now we're working without any experimental map, so on the Sim Settings tab I'll switch over to Free mode. This will trigger ISOLDE to do some preliminary analysis of the first loaded model to get it ready for simulation. Starting a simulation is as simple as selecting anything from a single atom to the entire model and clicking Go, keeping in mind that for interactive performance the selection size should be kept reasonably small. Here I'll just go ahead and select the entire model. One of the big challenges of model building in general lies in the fact that even to the experienced eye it can be very difficult to tell a reasonable arrangement from a wrong one. This challenge is compounded when the atoms are actively moving, so a lot of my effort in designing ISOLDE has revolved around finding ways to make things more intelligible. A particular focus is on providing real-time visualization of common geometric problems. The first of these is this traffic light style visualization of the alpha carbon atoms, which continually updates to give the current status of each protein residue on the Ramachandran plot. Residues in favored conformations are colored green, while the remainder shade from yellow to dark pink as they become more unlikely. Unlikely sidechain conformations, or rotamers, meanwhile, are annotated with this exclamation mark spiral motif. These appear only for rotamers outside of favored conformations, and change both size and color according to severity. You may be wondering about that cyan atom in the middle there. That one has nothing to do with validation. It's highlighted because it's currently closest to the tip of my 3D haptic interface, which is represented by the little green cone here. Being able to interact with the model in true 3 dimensions like this certainly makes everything much easier, but it's just one of the options for model interaction in ISOLDE. Most of your day-to-day interaction with ISOLDE will be through the addition and removal of temporary restraints to guide the simulation into new conformations. Let's start with rotamer manipulations as an example. Selecting an atom in a protein residue enables the rotamer tools, allowing you to cycle through previews of a probability-ordered list of ideal rotamers. Once you've made a choice, you can click Commit to simply set the new coordinates, but in many cases I find it preferable to instead click Set Target to force the existing coordinates towards the new conformation. This approach has a substantial advantage of never introducing atomic clashes, allowing the surroundings to adapt naturally to the changes. The dihedral restraint mechanism used for this task is also used for restraining secondary structure and when flipping peptide bonds. It's of course important to always know when you're applying artificial restraints and how well satisfied they are. So to visualize dihedral restraints, I settled on this ring and posts motif, using both color and geometry to show the level of satisfaction of each restraint. Peptide bond geometry controls are found just above the rotamer controls, and like those are only available when a single mobile protein residue is selected. These are implemented strictly as dihedral targets for the same reason as rotamers, that is, the avoidance of very high energy and possible conformations. In this case, the applied restraints are temporary and will be released when the flipped conformation is reached or if it proves impossible to reach after a few dozen simulation steps. The cis-peptide bond, where the hydrogen and oxygen are on the same side, is an exceedingly rare natural conformation in non-proline residues and is flagged with this red filled-in plane visualization. All peptide bonds in ISOLDE are restrained by default so that this type of flip cannot happen by accident. While individual atoms can be tugged directly using the keyboard and mouse, this can be difficult to do accurately due to the unavoidable fact that a mouse can only tug in the two dimensions perpendicular to the direction of view. For large rearrangements, therefore, it's often easier to make extensive use of temporary position restraints, which can be accessed at the bottom of the Rebuild tab. These are also useful in various other situations, for example for keeping side chains away from unfilled ligand density. If you're particularly eagle-eyed, you may have been wondering why this IGF-1 model is missing its disulfide bonds. I've made it that way on purpose so I can show my two favorite tools. But before I do that, this would be a very good time to mention the checkpointing function. This allows you to save a snapshot of the current state of the running simulation, including the coordinates and all current restraints, and return to it discarding all subsequent changes if you make a mistake. This can be particularly valuable when testing hypotheses about different possible conformations of a problematic region. Now, on to secondary structure restraints. These combine dihedral restraints with atom-to-atom distance restraints to force the peptide backbone towards defined conformations, parallel or antiparallel beta strands or alpha helices. These are soft enough to still allow reasonable flexibility, but generally do a good job of attaining the desired conformation even when it's a very long way from the starting conformation. Like, say, if I wanted to turn this entire IGF-1 molecule into an alpha helix. Notice that the imposition of all these extra restraints doesn't impact on your ability to interact with the model. You can still pull it around with your mouse or haptic device as much as you like. And now you know what IGF-1 looks like as an alpha helix. Just to really demonstrate this, I'm going to briefly turn Chimera X's cartoon representation back on and recalculate secondary structure using the DSSP command. Once done playing, just click Return to Checkpoint and it's like it never happened. The next tool I'd like to show is the register shifter. While particularly fun to watch, it has a serious purpose. At the resolutions ISOLDE is designed for, errors in register, where stretches of peptide have been assigned one or more whole residues away from their true positions, are not at all uncommon. In ISOLDE, any continuous stretch of peptide residues can be told to shift smoothly forward or backward along their length, making the task of recovering from such errors quite straightforward. Moving on to a real-world example, discussed in much more detail in my upcoming paper on ISOLDE. 3JA8 is a cryo-EM model and the first published structure of the eukaryotic MCM2 helicase. At around 5,500 unique residues and a resolution of 3.8 angstroms, it's a large and challenging beast, and at a first glance the PDB validation statistics look pretty good. Okay, the high clash score looks a little problematic, but nothing stands out as an obvious red flag. Before I get properly started, a few housekeeping details. To prepare the model for simulation, I've used an external package to add in the many missing sidechains. Remember, all residues must be complete for ISOLDE to work. I've also removed the ADP ligands, since these are not yet supported. I'll be using position restraints to keep the surrounding residues out of the ADP density, and add the ligands back in when passing the final model out to Phoenix RealSpace Refine. Since now we're working with a real experimental map, we'll be running in map fitting mode. In this case, we need an MTZ file with at least one set of map structure factors. If, as in this case, you're working with a real space map, you can easily convert it using Phoenix map to structure factors. Or why not use Phoenix Auto Sharpen to improve the map interpretability at the same time? Pressing the Initialize button prepares your map or maps, and also triggers preparation of all dihedrals, rotamers, etc. in the model. For a model this size, that will take somewhere between 10 and 30 seconds. When done, the representation will change to a minimalist cartoon and a scrolling sphere of density, which should be familiar to users of existing crystallographic visualization and model building software. In this mode, the mouse scroll wheel changes the map contour level, while dragging with the right mouse button zooms the display and dragging with the middle button pans. If you have multiple maps, you can choose which one responds to the scroll wheel by scrolling with the Control key pressed. I strongly recommend switching your density map to a transparent surface representation as shown here. Note that particularly for cryo-EM maps, you'll need to adjust the coupling constant between map and simulation using the map settings dialog. At present, this is a somewhat ad hoc affair, but a reasonable heuristic is that the coupling constant times the map 1 sigma value, which you can get from the lower left of the Chimera X window when adjusting contours, should be in the range 1 to 10. The first thing we need to do when working with a new model is to run a short simulation of the entire structure. This gives the molecular dynamics engine the chance to minimize out the worst of the high-energy features typically found in low-resolution models. It's particularly important to resolve any clashes, since these lead to exceedingly high energies. It's not at all uncommon for deposited models to have initial calculated energies in the tens of millions of kilojoules per mole. Starting the simulation triggers the map to be expanded and masked to cover the entire mobile selection. If you like, you can adjust the masking radius in the map settings dialog, but keep in mind that the mask will be updated regularly during the simulation, so the atoms are always in context even after large movements. I'm running this simulation with the Ramachandran plot visible because this is the first indication that this model is a bit more problematic than it might first seem. What we see is an immediate explosion of Ramachandran outliers. This isn't a failing of ISOLDE, but a consequence of the fact that this largely hand-built model was refined with the Ramachandran restraints. The problem with Ramachandran restraints in general is that they don't know where in the plot any given residue belongs, but will simply force it towards the nearest allowed region. What we see here is a consequence of the many clashes and unfavorable electrostatic interactions in the initial model pushing atoms away from each other. Sometimes a model has to get worse before it can get better. While we're looking at the Ramachandran plot, note that clicking on any point in the plot will take you straight to the corresponding residue in the main display. Clicking through a few of the newly introduced outliers, we quickly come across a non-proline cispeptide bond, another red flag. Clicking the green Keep Changes button stops the simulation and reverts to the standard scrolling display. The rotamer and cispeptide bond annotations from the simulation remain visible, and they certainly tell a story here. It turns out that this model has over 100 spurious non-proline cis bonds, and the number of rotamer outliers has increased from that seemingly perfect initial 0.1% to somewhere approaching 10% of residues. Since cispeptide bonds are such rare and unusual features and can do strange things to the backbone conformation, checking and when necessary correcting these is a natural first step in the remodeling process. This can be done conveniently using the peptide bond validation tool found underneath the Ramachandran plot on the Validate tab. Like with the Ramachandran plot, clicking on any entry in the list will take you to that residue and select it. In most cases, simply clicking Go will give you a localized simulation big enough to deal with it, but it's always a good idea to look for signs of larger scale problems and if necessary stop the simulation and restart with a bigger selection. While correcting these, it may be worthwhile to fix any other obvious problems you see, but I wouldn't recommend spending too much time wrestling with individual residues at this stage. First, it's important to remember the golden rule. Human eyes should see each and every residue in context at least once. In other words, we need to go through the model looking specifically for large-scale errors. There's no point spending all your time tinkering with the details if some large-scale change is going to wipe out all your hard work. Looking for large-scale errors like register shifts requires a different style of visualization. Rather than focusing on individual residues, we want to be looking at substantial stretches at a time, with just enough surrounding density to give them context without becoming overwhelming. Currently hiding away at the bottom of the Sim Settings tab is a tool for this purpose. Clicking Step Forward will go to the first pair of defined secondary structure elements and isolate them, along with their flanking unstructured connections. Each click will step forward in an overlapping sequence, allowing you to relatively quickly cast your eye over the whole structure. Remember, at this stage you're looking for signs of serious error. By all means, feel free to correct any obvious smaller scale errors that you find, but it's counterproductive to spend significant time on challenging spots until you're sure the surroundings are not going to change substantially. Doing just that after clearing away all the cis-peptide bonds, and have come across this interesting problem. In the middle of chain 4, we hit a one residue break in the chain, where the sequence jumps straight from lysine 467 to valine 469, with no room for the intervening lysine residue. I can only assume that this came about due to an error in sequence alignment when generating the initial homology model, but it has gone undetected and led to a register shift in the following stretch. But how far does this shift reach before the sequence pops back into register? The only way to find out is to carefully inspect the following residues for poor fit or unlikely contacts. Examples of what we're looking for here include over or underfilled side chain density, hydrophobic side chains making close contact with charged ones, or poor backbone fit to the density, particularly where the backbone appears overly stretched or bunched up. This leucine residue seemingly attempting to make a salt bridge with an arginine side chain is a particularly clear indication that this helix is out of register, and as we move up we can see that the fit to the following loop isn't all that great. So we can suspect with some confidence that the register shift extends at least to here. So let's start up a simulation covering this stretch and give it a try, keeping in mind that ISOLDE's checkpointing function ensures that we can play with different possibilities without fear of permanently damaging the model. You can make the necessary selection using Chimera X's command line selection syntax if you like, or you can take advantage of its handy selection promotion mechanism. If you select a single atom, then pressing the up arrow will expand the selection first to the whole residue, then to the whole secondary structure element or loop, and then to the whole chain. Selecting one atom from the helix and each of its flanking loops, then pressing up twice, will give you a simulation-ready selection. To induce the register shift, we start by selecting an atom from valine 469, then using the tools in the register shift dialog to expand the selection towards the C-terminus until it reaches our hypothesized end. Once you're satisfied with the selection, set the size of the shift to 1. Remember, a positive number indicates a shift towards the C-terminus, and click Make It So. I recommend leaving the shifting restraints in place until you've had a chance to look over the length of the shifted region, but when you're satisfied, just click Release. Remember, it's still not necessarily a good idea to attempt perfection at this stage, while there's still the possibility that there are other large-scale errors in the surrounds. Once you're satisfied that the result is essentially correct, or at least more correct than before, it's best to move on, then come back later for the finer scale cleanups. Jumping forward a bit, let's take a look at a few before and after stills of this region. Where valine 469 was previously, we now have lysine 468, nicely filling the density and forming a neat double salt bridge with aspartic acid 431 and glutamic acid 497. Over on the helix, we can see that the implausible contact with leucine 485 was pushing arginine 428 well out of density, but after the shift, the arginine now comfortably continues the complex salt bridge with glue 497 and continues it to glue 484. There are various ways you can approach the remaining cleanups, but that's really a matter of personal preference and the available computational power. One, the approach I took in this case, is to use the Ramachandran plot, tackling one outlier at a time. This may seem like a daunting task, but keep in mind that in the act of solving one, you'll often end up solving another half a dozen nearby, so it's not as big a job as it might first seem. The other is to once again work through systematically end to end, this time focusing on all those details that you brushed past the first time. Since this all boils down to repeated applications of the tools that I've already demonstrated, I won't bore you with it. Instead, let's jump forward to the results. On the top, we have the PDB validation sliders for the original deposited model. On the bottom, we have my result after about a week of work in ISOLDE combined with tightly restrained refinement in Phoenix RealSpace Refine. Obviously an improvement, but a simple glance at these might leave the naive viewer asking, why did it take a whole week to do that? After all, the changes in any one metric are only a few percent at most. Perhaps this will make things clearer. Here I've plotted the changes in the key peptide backbone dihedral angles phi, psi, and omega, as well as the root mean square bulk movement for each residue in the model. Almost a fifth of all phi and psi dihedrals have changed by more than 45 degrees, and almost 8% of all residues have moved more than 2.5 angstroms. All in all, just under a third of all residues in the model have had a substantial change in at least one of the listed criteria. To top things off, in keeping with my observation at the start that there is little to no correlation between fit to data and model quality at these low resolutions, we can see that despite these extensive changes, the Fourier shell correlation curve between final model and map is essentially indistinguishable from the original. I've developed ISOLDE with the generous support of Professor Randy Reed and the Wellcome Trust. ISOLDE is dependent upon Kevin Cowden's Clipper libraries, the wonderful OpenMM Molecular Dynamics library from Stanford, and of course Chimera X from UCSF. I would particularly like to acknowledge the extensive help I've received from Tom Goddard of the Chimera X team.